All right, welcome to the problem solving portion of the periodic trends video series. I've got two problems for you, only two because the last video was pretty long, and so we're just going to bang these out real quick, okay? So they're both from the book. They're both problems that are assigned to you in the problem set, so I'm reducing your workload ever so slightly. The first problem asks about size or atomic radius. That's one of the properties we discussed in the previous video. And the next problem asks us about ionization energy. Okay. Once again, like I did mention in the previous video, there are some questions on electron affinity, but I'm going to leave it up to you to sort of figure out electron affinity based on all the things that we've talked about. Okay. So no example problems on that just yet. All right, so chapter 7, number 111, arrange the following groups of atoms in order of increasing size: potassium, bromine, and nickel. All right, so we've got potassium, bromine, and nickel, and we're supposed to order these elements in order of increasing size. Okay, well, let's take a look at the periodic table. Let's find where these elements are. We've got potassium here, krypton, nickel. Okay, those are the ones that we're looking for, right? No, bromine, sorry. So potassium, bromine, and nickel. Okay, so they're number 19, number 28, number 35. These elements are all in the same row. I do want to make a little comment about that. It is more than likely going to be the case that whenever you're asked to compare elements in terms of these different properties, atomic radius, ionization energy, electron affinity, you're more than likely going to encounter sets of elements that are either all in the same row or all in the same column. And that is because it is somewhat unfair and honestly really difficult to compare elements that are neither in the same row nor the same column. Okay, so like, show you this one more time here. It would be unlikely for you to be asked to compare iron with gold, for example. Iron and gold are not in the same row or the same column, and so you can't really apply the principles that we've learned about recently. Effective nuclear charge, things like that. You can't really apply those principles to come to concrete answers in terms of these properties here. So, like I said, potassium, element number 19, bromine, number 35, nickel, number 28. These are all in period 4. Okay, so they're all in row 4 on the periodic table. So the question is, right, how do we arrange them in terms of increasing size, right? So we're trying to go from smallest to, I guess, medium or middle to largest. Okay? And if I were to actually arrange these elements as they look on the periodic table, looks something like this, right? We've got potassium over here, number 19, nickel sort of in the middle, and then bromine was way over here, number 35. Okay, so, sorry, my phone is going off here. Move this away. Okay. So, at first glance, you might be thinking that bromine is the biggest, right? It's got more protons, more electrons, presumably more neutrons as well. It's got the biggest atomic number. It has the largest atomic mass. So we might think that that's the largest of these three. Well, before we go with that, let's think about what actually determines the size here. Okay, so these elements are all in the same row. Okay, let's look at where their last electron is. Okay, where the final electron is, or put it this way, let's look at the final term of their electron configuration. So the final term in the electron configuration for potassium is 4s1. The final term in nickel's electron configuration is 3d8, and before that is 4s2. Okay, and then the final term in the electron configuration for bromine is 4p5. And prior to that is 3d10 and 4s2. Okay, so I've done a little bit of extra work there. Okay, okay. So our final electron is in those orbitals there. What I want to illustrate here is that in elements of the same row, your final electrons are not increasing in terms of valence level. Okay, so right here, the final electron is in the fourth energy level, right, or the fourth valence level. Your final electrons here are, I mean, technically in the third, but we still have these two, right, that are in the fourth level. So the outermost electrons are in the fourth energy level. And the same thing here with bromine. Okay, so in all three cases, the electrons are in the same valence level, like the outermost electrons are in the same valence level. Okay, the other thing that we should think about, the other thing that we should consider is their atomic number, right? What does the atomic number tell us? Well, the atomic number is the number of protons, right? In addition to being the number of electrons in a neutral atom. But for now, I mean, think about that. That's the positive charge in the nucleus, right? The amount of positive charge in a bromine nucleus is nearly double that of the positive charge in a potassium nucleus. That's really important. So in the video, when we talked about the trend for effective nuclear charge, right, the overall amount of force that valence electrons feel towards a nucleus, the trend was actually that the effective nuclear charge increased in this direction from left to right. Okay, so more effective nuclear charge here than over here, and then this would be in the middle somewhere. And that's due to that larger amount of protons, that higher magnitude of positive charge, while the valence level is not increasing, right? The valence level stays constant here, right? The outermost electrons are in the fourth energy level. What that means, okay, because the effective nuclear charge is increasing from left to right, the size of the atoms actually decreases as you go from left to right, okay? This nucleus here, the bromine nucleus, because the magnitude of the positive charge there, because the effective nuclear charge here is so much larger than it is over here, or even here, the electrons feel a stronger attractive force. And so they position themselves, or they are arranged then somewhat closer to the nucleus due to that higher attractive force. Okay, so bromine actually is the smallest of these three. Okay, and you can sort of backtrack your way towards the left here. Nickel would be medium, and the largest atom, somewhat unexpectedly, is the first element in the row, which is potassium. Okay, so even though it's probably got something like half the mass of bromine in terms of its volume, right, the amount of space it takes up, its actual size, potassium is a bit larger. Okay, I haven't looked up the actual values here, but if you wanted to do that, look up the atomic radii of these three elements, you would see that this matches with what the data actually shows us or tells us. Okay, so that is the first problem there. Let's go back to the slides and see if we can take a stab at the second question. Okay, all right, so on to number 116 in Chapter 7. In each of the following sets, or in this particular set, which atom or ion has the smallest ionization energy? Okay, so we have a -2 sulfur ion, a neutral atom of sulfur, and then a +2 sulfur ion. Okay, well, these can be a little bit tricky, so because not only are we working with something a little bit less visual, like something harder to visualize, right? Ionization energy is a bit harder to visualize than atomic radius, but we're also just dealing with ions rather than just like completely different elements. So these are ions of the same element. All right, so that makes it a bit more difficult. All right, and we're looking for the element, or the ion, I should say, the atom that has the smallest ionization energy. And I'm going to go ahead and rewrite that as easiest to remove an electron from. Okay, these mean the same thing. Okay, having a small ionization energy means that it's easy to ionize. Okay, and ionizing means removing an electron. Okay, so the smallest ionization energy is going to be whichever one of these we determine is the easiest to remove an electron from. Okay. There are a few different ways you can come at this. What I'm going to do is I'm going to actually take a really close look at the electron configurations for these three atoms or ions. Okay, so I'm going to make myself a little bit of a table here. The first part of my table, let's actually talk about how many electrons there are in each of these. So a neutral sulfur atom, sulfur is number 16, by the way, on the periodic table. A neutral sulfur atom is going to have 16 electrons. Okay, so in this part of this column of my table, number of electrons 16. Now, if it's a -2 sulfur ion, this is still sulfur, okay, which means it still has an atomic number of 16. So there's still 16 protons, but the ion overall has a -2 charge. That must mean there are 2 more electrons than protons. Okay, so for a negatively charged ion, you have more electrons than protons. Okay, and then vice versa, or sort of the opposite of that, I should say. Sulfur +2 ion, this means that there's more protons than there are electrons. And we know that there have to be 16 protons, right? Because the letter S here says, hey, this is sulfur, so this has to be 16 protons, therefore 14 electrons. Okay. What I'm going to do next is I'm going to actually go through the work of writing down the orbital diagrams, okay, for each of these. Okay, so that's these boxes here. Okay, let's see. This is going to take me a little bit of work, but I assure you it will be worth it. This is going to be 1s, 2s, 2p, 3s, 3p. And I think that's as far as we need to go. It's 3p. All right, so let me go ahead and get this all set up so I can do this nice and quickly. Maybe I should have prepared slightly before I started the video, but it's okay. Sometimes you start a problem and you just don't know where it's going to take you. Okay. So let's go ahead and do this for 18 electrons here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, so I've got a completely full first 5 orbitals there. All right, and notice how I put these arrows in, right? So they go in so it's easy here for like the 1s and 2s orbitals, but when you get to the 2p orbital, right, the rule is, right, you just have to sort of do it one box at a time. Then once each box has an electron, you can go through and fill in the others, right, pairing them up. All right, so this is 10, 11, 12, 13, 14, 15, 16. Okay. And then we get to the sulfur 2+ ion. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh boy. Okay. So one thing I want us to notice is that in all 3 cases, the electron configurations that I've boxed in over here, 1s through 3s, identical. Okay? So it's very, very unlikely that this part of the electron configuration is going to have any role in our explanation of why the ionization energy in these might be bigger or smaller. Okay? This over here is where we actually observe the difference, right? The 3p orbital in each of these ions looks very different, okay? Completely full, sort of like half full, and then less than half full. Okay, one other thing I do want to note is that in all three of these ions, we have 16 protons, okay? I've already mentioned that, but these are all sulfur, okay? So the amount of positive charge in the nucleus is the same for all three elements, okay? Or is the same for all three ions, I should say. Okay, so let's think here. In which of these cases would it be easiest to remove an electron? Okay, and we're talking about a valence electron when we say that. So, in which of these situations would it be easy to remove an electron? Easier. Kind of difficult when you think about it. You could make an argument that perhaps here it would be easiest. Why? Well, because if we look at one of these electrons, say this guy has 5 other electrons in the same orbital that are going to be repelling that electron away, okay? Whereas if we look at, say, this guy, he only has 3 electrons that are repelling him away, and this guy only has 1. I believe that ends up actually being the explanation, okay? It's due to the electron repulsions. The reason I made a point about there being 16 protons in each of these is to illustrate to you that this can't really be a factor in terms of explaining the difference between these, right? This whole electron configuration section was the same. The number of protons is the same. The only thing that's different is the electron configuration of the outermost orbital there, or the highest energy orbital. Well, Mr. Akampora would get upset with me saying highest energy orbital. The 3p orbital. I'll just leave it at that. Okay, this is the only place where we have a difference amongst all of these 3 different atoms or ions. So, and once again, let me go through that explanation. The reason that this guy would be easier to remove than this guy, which would then in turn be easier to remove than this guy, they're all 3 feeling the same sort of positive force, okay? But this one is feeling it is feeling 5 electrons worth of repulsion from its buddies in the 3p orbital. Okay, so 5 electrons worth of repulsion, 3 electrons worth of repulsion, only 1 electron worth of repulsion. Okay? So I'm going to go ahead and say that the one with the smallest ionization energy is sulfur 2-. Okay? And I'm going to end the video, and I'm going to go look it up, and if I'm wrong, I'm going to have to re-record the video. But if I'm right, and you hear this, then sulfur 2- does in fact have the smallest ionization energy. I hope that's the case, because I don't really want to have to record the video again. All right, well, that's it. Look forward to seeing you guys in class on Friday. Thanks for watching.